First of all, if I go to the assignment, so I did give you access to the non-graphing utility. Okay, well, it might be good. Okay. Everybody knows what that is, right? That's the, if you hit NGU, with each of these, on each of these pages, whoops, on each of these pages, oh, did it mess, what? Oh, never mind. There we go. This guy. There it is, yeah. 12 or 13? Okay, let's look at these. If I do go back to that last one though, so did everybody see that all we're really doing here on this one is they're giving us, it doesn't matter, they call it a polynomial, but don't worry, that's language that we'll talk about later. You may or may not even know what a polynomial is. I don't care, it's not important. But they give us some function. C of x, so we're using function notation, right? C of x equals this big long expression involving x's, where x represents the number of years after 2005. So in a problem like this, if we're trying to figure out what this model predicts, this is a model for production costs, what it predicts for the year 2011, what value of x is represented by 2011? 6, okay, because we're looking at the number of years since 2005. So this corresponds to x equals 6, right? So what we're really doing is we're evaluating C of 6 to see what that gives us. So what's that mean? Well, we're just plugging a 6 in for all the x's, okay? So here's what I'm going to recommend on this. What I probably should have done in hindsight is I should have probably made the Desmos graphing calculator available. And feel free to use it. But go ahead and bust out your TI-84s for a second, because I want to show you something really helpful.
Yeah.
Okay, so on your TI-84, there's a way to make this pretty simple. I'm going to show you lots of tricks this year on the TI-84. Let me... Oh, it's going to be awkward, isn't it? Okay, so there's C of x, okay? Here's what you can do on here. You can go to home. I'm in some weird place. I've been doing some graphing stuff. So if I go quit and I get to the home screen, you can type in this whole expression with x's and everything. So we're going to type this in. So we get 10, you can do this with me if you want, 10.23 x, and then there's the symbol for an exponent. Everybody see that? We're by right down there. That's how you get an exponent. X to the 5th. And then you got to hit the right arrow to get out of the exponent position. Minus 165.68 x to the 4th. Okay, I'll scoot over here so we can see the rest. Scoot to the right. Plus 1918.24x cubed minus 7740.01 x squared. And when I do the squared, this is a little bit of a shortcut. There's a squared button right there that puts it up in the exponent and moves you back down. Okay, so it's a little easier. Plus 5740.01 6.5x plus 74100, right? Is that it? Yeah. Okay, and I'm just going to hit enter. It gives me some random number, who knows why. Here's why. We can store a value of x in the function and then go back up and figure out what that expression would give me for that particular value of x. Here's how you do it. We want to choose the value x equals 6, right? So I'm going to type 6, and then down at the lower left there's a store button with an arrow by it, arrow to the right. You see that button? So I'm going to go 6 store x and then hit enter. And so the calculator now stored the value 6 as the variable x. It gave it that value. So if I go up with the up arrow until I grab that expression, that big long expression that I wrote, and I hit enter, it's going to pull that expression down. And now I'm going to hit enter again, and it's going to tell me what the value of that expression is when x equals 6. How about that? Okay, so that's my answer. Okay, if I fill in the correct response. You guys unfortunately don't have that. But if I fill in the correct response, once it rounded to the nearest dollar, I would round that up to a 6, wouldn't I? So there's the answer, 108,866, which is what we get from the calculator. Doesn't make any difference. The radians and degrees would only matter if you were doing trig functions like sines and cosines. Right, and you really, we won't, not until the very end of the year, if even then, will we do anything where you'd have to worry about that moment. Okay. Okay, so that's how you can do that really conveniently on your calculator. Now I'll show you on your Chromebooks. Why don't you go ahead and go to and bookmark this, because you'll use this a lot. Let's go to the Desmos graphing page. And to get there, I'll show you how you get there. If you just, for the first time, if you just Google Desmos, and then as you start to type Desmos, it'll come up with Desmos calculator, or even better, Desmos graphing calculator. So that gets you here. And then bookmark that. And what I would even do if I were you, you don't have to do it right now, but I would make an account. Because this will be handy. In this class especially, there'll be a lot of times where you might save some graphs and want to go back to them later. Like make some templates for functions and want to go back and reuse them. I do that in this class, but even more so in my AP Calculus class. And I mean, look at this list of stuff I've built here. I've got all these things I go to from my classes that I pull up. There's a big long list, and then there's 65 more I can add, right? So there's all these Desmos files that you can reuse if you want it. Okay, so here's what we do on this one, though. It's a lot easier on Desmos. So on Desmos, we're going to define a function. So we're going to call this, I'm going to call it capital C of x equals, and I'm just going to type in everything exactly like I've got right there. And it's easier on Desmos. It's more intuitive. So everybody do this. 10.23 x, and then you just go shift 6. That's the exponent key, shortcut to get up there. Shift 6 to the 5th, right arrow, minus 165.68 x to the 4th, and so on. Type in that whole big long function right there. Okay, and you can kind of drag this thing over so you can see the whole thing. You don't really need the graph. It graphs it, but who cares? We don't really need that. We just need the function in there. Okay, everybody there? I'll wait just a little bit for everybody to get that function in so you can see this magic happen before your eyes. Everybody agree? The value we wanted to plug in for the function was 6. So I'm going to go down and I'm going to the next line, and I'm just going to do capital C of what? 6. And what's it do? It tells me the value of the function when I plug in a 6. What's great about this is I can plug in any value I want to. I can just go back and change that to a 65 if I want to, right? Whatever I plug in, when I use the function that I've defined up here in this line, if I ever use that, if I evaluate that function for a specific value of x using function notation, Desmos is smart, it knows function notation, it's going to tell me what the output of the function is when I input a 6. And so the question tells me to round to the nearest dollar, so once again, I would just round that 108,865.68, I just round it to 866. Okay? So that makes big computational questions like that. Use technology. That's what it's for. Okay? So there's the first problem. Let's look at the others. All right. So what about these? Okay, what about this? So a rectangle has a length of 3x plus 3 and a width of 3. So first of all, they want us to come up with a function. Once again, ignore the word polynomial. Just come up with a function for the area of the rectangle. Well, how do you calculate the area of a rectangle? Yeah, length times width. So 3x plus 3, the quantity 3x plus 3 times 3, right? And I could just, so it would look like this, wouldn't it? We would get, for part 1, a of x is just going to be 3x plus 3 times 3. And if I want to simplify that, I could just distribute the 3, right? So that would just give me 9x plus 9. And then they say when the length is 15, what's the area of the rectangle going to be? Okay, but we got to figure out what x value goes with that statement. If we're saying that the length is 15, how am I going to figure out what's the x value that goes with that? This is kind of tricky.
3x plus 3 equals 15.
There you go. Good, because here's the length. It's 3x plus 3. So if we set 3x plus 3 equal to 15, I solve for x, I would subtract 3. So I get, what, 3x equals 12, so x equals 4, right? So that's the value of x that I need to plug into my function. And so if I plug 4 in, what would I get? Like, what, 36 plus 9, so 45? Okay, makes sense? Okay, and then, what about the last one? I think it's just kind of more of the same. Oh, yeah. Okay. So this time they're telling us that here's the area of a circle in terms of radius, right? So we could write that, if we wanted to write that as a function, we could write that as a of r if we want to. A of r equals pi r squared. Isn't r the input for that function? I'm plugging in a radius to calculate my area, right? Okay, so that works fine. But they're telling us now that we want the radius to be given by 1/4 x. So we're saying r equals 1/4 x, which I could just write as x over 4 if I wanted, right? So if I want to come up with a new function, a of x, what do you think I'm going to do? What do you think I'm going to do there? They're challenging. But where I used to have a radius, they're telling me now that the radius is going to be x over 4. So yeah, I'm just going to rewrite that whole thing, aren't I? So I'm going to end up with my area, instead of instead of my area being pi r squared, if I write this, if I make that substitution where r is replaced by x over 4, right? I would just be plugging x over 4 into for my original radius, and that's what I'm going to get. Well, if I square x over 4, what do I get? If I square a fraction, how do I do that? You remember? And you might have noticed on the assignment, these are only worth a few points. I mean, they're kind of the challenge questions at the end. Don't really affect your grade very much, but they're just there to really challenge you. What happens? What's 1/2 squared? What is it? Think about that. What's 1/2 squared? Well, yeah, 1/2 squared is 1/4, isn't it? Because I'm squaring the 1 and I'm squaring the 2. What if I do 2/3 squared? What's that? 4/9. 2/3 times 2/3. So I'm squaring the 2 and I'm squaring the 3. So what is x over 4 squared? X squared over 16. Good. Right? So then we'd end up with my area function is just going to be a of x is just going to equal pi x squared over 16. Okay, see that? All right. Moving on. Okay, so this is, for you guys, I'm not going to make a quiz out of this. I don't need to do this for the honors class. But my other classes, they're going to have a little quiz tomorrow, and they have to be able to demonstrate for me that they can do all this stuff. We're not going to take time to do that, but I want you to be able to do all this stuff. Does everybody, and now's the time, raise, if you're not sure, I guarantee somebody else has the same question. Everybody knows how to log into Moodle. Everybody knows how to go to the Algebra 2 page, right? You should bookmark that. Everybody knows how to open a homework assignment because you've been working on them. Do you know where to find the due dates? On the calendars. Everybody know where to find the calendar? Okay. Any questions on that? Okay. Do you know where to find all the resources? Can you find, when I say textbook resources, I mean the specific resources for each assignment. You know where to find those?
Isn't it the
PDF.
PDF.
Yeah. Right, any of the links that are in that section above the assignment. Usually there's going to be like 2 or 3 little spots where you can go to find. So that's quote unquote your textbook. That's where you can go to find information that you might need. Instructional videos and notes, you know where to find those? Anybody not sure? Okay. Anybody? I'll show you real quick if you have a question. Okay, good. All right, so for today, go ahead and click those closed. We'll be pretty quick with this, but I want to show you some pretty important stuff. Now, the fact that it's not very difficult doesn't mean it's not important, because what I'm going to show you now, we can extend to harder stuff later. So click those all the way closed. I know there's a temptation, you're getting stuff done, and that's all good, but I want your attention now, so click them all the way closed. So today we're going to look at solving simple equations. In the handout, you might notice in the upper left, they give you sort of a reminder of the basic steps to follow. And they're good, but I'm going to show you a better way to do it. Better way to think about this is by using order of operations. And this is once again, this is a really simple thing to think about, but hugely important. And here's the thing, you're such good math students, you're probably, well, I know you're doing all this stuff without thinking about it. But here's the danger with that. Sometimes if you're just doing something because you already know how to do it, what happens when we extend that to a much harder classification of function, for example? Something other than just a linear function, where we got to solve an equation. Then all of a sudden, all those things that were so easy for solving linear equations become more difficult. And if you don't know the process that your brain was actually using, it's difficult to make that jump. So I want to sort of show you what you're already doing without knowing it. So our order of operations tree, we reviewed last week that when we want to simplify some kind of an expression, whether it's numerical or if it's got variables in it and it's algebraic, we just use regular order of operations direction. Now I mentioned last week that if we want to isolate a variable, so we're going to solve an equation, which is the same thing as isolate a variable, we're going to reverse the order of operations. Here's the rule. We're going to simplify the equation until you can point to a single variable, and as soon as you can, we turn around and we reverse the order of operations to solve for that variable. This is all stuff you already know how to do, I promise you. Let's take a simple example, something like this. What's the first thing you would do if you're going to solve this equation? You distribute the 7 first of all, wouldn't you? Okay? Without even thinking about it. Well, here's why you're doing that. The reason you're doing that is because, would you look up here and notice that there are 2 instances of the variable x? It shows up twice, right? You can't isolate a variable that shows up more than once. You can only isolate the variable when it shows up once in the equation, right? I'll say this about 1,000 times this year. If you can point to a variable, then you can isolate it in an equation, right? So the first thing we've got to do is we've got to simplify until we get a single x. Well, if you look at all the steps to simplifying this, are there any, look at the parentheses. There's only one set of parentheses there, x minus 6. Can I simplify x minus 6? No. So we can just skip right through that step. There are no exponents, so I can skip through that step. The first time there's anything I can do is the multiply divide step. Well, that's multiplying in this case means distributing, doesn't it? Right? So we'll distribute the 7, and there's our first step, is 7x minus 42 equals 10x minus 78. What would you do next? Without thinking about order of operations, what would your next move be? Yeah, good. Subtract 7x from both sides. So the way I like to talk about that is kind of visually. When you're looking at an equation, we always want to push the variable to the most convenient side. We're going to push it to the right where we have a larger number of x's, so we get a positive coefficient, right? You all knew that. Well, where does that show up? Add, subtract, right? The last step in simplification. So we'd subtract 7x. The 7x's cancel on the left. I get negative 42 equals 3x minus 78. Now this is a really simple example, but what would you do next? You'd add 78 first, and then what? And then divide by 3 to get the x by itself. Why are you doing that? Because now that we isolated the variable, we can reverse order of operations and isolate it, right? First step, add, subtract. You bet we're going to add 78. So the 78's cancel, and I get 3x equals, what, 36? And then last step you told me was divide by 3. How come? Because that's the next step. When we reverse order of operations. Divide by 3 and get x equals 12. So you knew what to do. Everybody in here knew what to do, but that's why you're doing it. You're following, there really is a method to your madness here. How do I know if I got it right? Plug it in. Yeah, because when you solve an equation, the word solve is really a loaded word in math. Solve means we're going to find all the values of the variable that make the original equation true. Well, there's only one value that works here, and the value is 12, right? To know if we got it right, we see if it actually worked. Because the point is, find the values that satisfy the equation, meaning make it true. Plug it in and verify that it works. Now I get, when you're doing Moodle homework, you're probably not going to do that, nor would I. Right? It's easier, you can reload any question and get full credit, so you're probably just going to try your answer, which is good. See if it works, and if it doesn't, you load up another one and get more practice. That makes sense. But I want you in your mind right now to kind of make a division, right? There's going to be a border. There's going to be kind of like the homework Moodle approach, and then there's going to be the test Moodle approach, which is different. On the tests, you can't reload questions. You miss it, right? So you got to remember to switch switch gears. When you're on the test, you got to make sure that whenever you're given an equation and you're solving an equation, always plug that back in. Why would you not? You'd be crazy not to, because then you can know if you got if you got it right or wrong every time, right? On high stakes tests, why would you not take advantage of that, right? Plug it in and see if it works. Okay. All right. What makes this harder? Fractions, and they really do. They really do make it harder. Fractions are just numbers, but they're inconvenient numbers, right? They make arithmetic much more difficult. Multiplying fractions is not such a big deal, but adding and subtracting is time-consuming. Got to get common denominators. It's a pain. So I want to go through something right now. This is, if you're really smart about your approach to solving equations, you can take a lot of the pain out of working with fractions, right? Any suggestions how we could just power through this, right? We could just follow the steps, push the x's to the right by subtracting these fractions, but can you already anticipate that if I go down that road, every step that I take is going to involve computations with fractions all the way through? We'd like to avoid that. What could I do to eliminate the fractions, to clear the fractions out of the equation? Multiply by 6. Yeah, and how come 6? Okay, because both of the denominators divide evenly into 6. Really what we're doing is we're going to look at all the denominators and figure out what would the least common denominator be if we were going to be adding all these fractions up, and multiply by that, right? So if we multiply by 6, you can already see, and I got to make sure I put everything in brackets, right? Because the 6 is being multiplied by each side of the equation. I'm just treating both sides equally, multiplying both sides by the same thing. When I distribute the 6, what's 6 times 1 6? 1. So the first term is just going to be an x. 6 times 7, 42. 6 times 1/3, good, 2x. And then 6 times 3. And now it's easy. I won't even go from there. Right, now it's a piece of cake. Okay? But that one. What number am I going to distribute through both sides? 40. Okay, how'd you get 40? Let's talk about that for a second. See, what's it? Go ahead. Any suggestions? I mean, and you're smart. You probably just saw that the least common factor of all those numbers is 40. But what if the numbers were more inconvenient? Those are fairly convenient numbers. There is a little bit of a logical way to approach this to make it a little easier. Which number up there is going to be the one that you're going to want to focus on first out of all those denominators? The biggest one. Yeah, the 20, right? If we're trying to find a least common denominator, think what that really means. The least common denominator is the smallest common multiple of all the denominators. So I'm not going to make this list, it'd take too long, but think about what it would look like if I were going to make a list of multiples for all of those denominators. For the 8, we'd get 8, 16, 24, etc. For the 5, we get 5, 10, 15, etc. For the 4, we get 4, 8, 12, etc. And for the 20, we get 20, 40, 60, etc. Do you see that the one that's taking the biggest steps is the 20? So it's easier for us, rather than look at all these big lists of all these multiples for the smaller denominators, just look at the multiples of the biggest denominator and see the first one that works for the rest of them, right? 4 and 5 both go into 20, but 8 doesn't. So that one we can take off our list. Move to the next one. Well, 40 works, right? So that's our number, okay? Now, next issue. There's a really cool way to, when you're clearing fractions like this, there's a cool way to do this where you can make the work easier still. There's another little trick. If I were to distribute that 40 through, for example, like what if I distribute the 40 through all the way through, like for example, 40 times 17/20ths. Yikes, that's going to be, what, 680 over 20. That's a pretty ugly fraction. 680 over 20, I don't feel like reducing that, right? You got to really think hard to reduce that. What could we do instead? And over here I would get 200 over 8, right? Those are big numbers to reduce. But keep in mind that when you multiply fractions, in order to get 680 over 20, what did we do? We multiplied 17/20ths times 40 over 1, right? When you multiply fractions, you can always cross-cancel to reduce. Agreed? So 17 over 20 I can't reduce, 17 over 1 is reduced, but what about 40 over 20? What's that reduced to? 2 over 1, right? Well, that makes it a lot easier, doesn't it? Now when I multiply straight across, I'm just going to get 17 times 2 over 1. I just get 34. I got 1 in the denominator. Okay, so is that an accident that I just happened to pick the term where it's going to work? It's guaranteed to work with every term. Think about it. It has to, because that's why we picked the number 40, didn't we? We picked 40 because that was a number that all of these denominators divide into evenly. So you always can take advantage of that. It's much easier to reduce first and then multiply and keep the number small instead of getting these enormous fractions that you have to reduce, right? So here's a way to represent that. You know that 40 over 8 is going to reduce. What does it reduce to? 5. Yeah, 40 over 8 is 5. So let's cross out the denominator and just multiply 5 by the numerator. What do you get? 25x, right? 40 over 5 is 8. So cross out the denominator and multiply 8 by the numerator. Aha. 40 over 4 is 10 times the numerator, 30x, right? 40 over 20 times 17, 34. Now it's easy. Right, in one quick step, we get rid of all the fractions, and now all the algebra from there on out is easy, no fractions. Right? And you'll see, if I push the x's to the right, like I would, so the x's cancel, and I get negative 24 equals 5x plus 34. What are the last two steps to solve for x? Subtract 34, good. So 5x equals negative 58, and then divide by 5. And so, yeah, I get x equals negative 58 fifths. I get a fractional answer, but I never had to battle a fraction the whole way through, right? It's a good trick, okay? All right, why don't you, what are we out of here, 10 after?
Yeah.
10? Okay, do that real quick. Do that one. Get a little practice doing that once. Shouldn't take long. Okay, what's our greatest common, or least common denominator? Smallest number they all divide into. 72, all right. Okay, so if I'll do my little trick here. When I distribute the 72, what's gonna happen? Good, 72 over 9 is 8. It's good, so I get negative 8n, right? Next term, 72 over 8. 9. So, plus 9. How about over here? 72 over 6 is 12, good. Times negative 5. Negative 60, good. And 74, or 72 over 24. Times negative 5. And now it's easy. You can take it from there. No biggie. Okay, what happens, what's different here though? Last issue. We gotta wrap it up. Okay, yeah, I've got a fraction that's being distributed, so what do? Right? There are ways where you could just clear the fractions right away, but multiplying fractions is easy. It's really not a big deal. You multiply straight across. So really the easiest way to deal with this is just to distribute the 1/2 first and then clear fractions, right? So if I distribute the 1/2, I'm going to get 7 over 16. So 7/16 Over here I'm going to get what, 3/8? And let's get rid of that x. That wasn't supposed to be there. Erase that. So minus 3/8 equals, and then over here is nothing to do. Right? And now I would just do like I've been doing, with fractions. Okay? So here, what would you do? Yeah, just distribute the 15/16, and you can reduce. While you're distributing, you maybe can reduce some stuff, right? Cross cancel. But distribute the negative 15/16 and then clear fractions if necessary. Okay? How about there? Distribute the negative 1/3 and then clear fractions. Right? Even if there's only one term of the fraction, do it. It's worth it. Okay, last one. I guess I lied. Here's the last one. So what about a ratio like this? If you got a proportion, a ratio equation, right? Fraction equals fraction. These are really simple. You don't even have to worry about clearing fractions. What do you always do if you're solving your proportion? Cross multiply. Exactly. So we could do this cross product. So 2 times the quantity 2z minus 7 would equal
3.
This cross product. So 3 times z minus 4. Just distribute it, it's easy. Right? We good? Okay.
We have homework tonight.
You do. There's new homework due